Okay, we're back. Sorry for a little bit of delay. This is the third session of the Material Appearance Modeling Workshop, and this will be followed by the Zoom session with general discussion. In this session, our first paper will be presented by Sebastian Merzbach, and so I will, you see him live here, will turn it over now to the recorded presentation.
Welcome to our presentation. I'm Sebastian Merzbach and I will present work by Klein and me at the University of Bonn in Germany. Recent years have brought efficient new ways of both measuring and artistically authoring new materials. Measurement devices like the Viso X-Tex or X-Rite's Tech 7 scanners allow for fast material acquisition with very little training effort. Software like Quixel Mixer or Adobe Substance Designer provide artists with sophisticated tools for composing realistic materials from existing resources or even from their own smartphone photos. Databases of materials that are ready for physically based rendering are now as available as texture databases used to be 10 years ago. Examples are Adobe Stock Materials, Polygon Textures, or the Quixel Megascans. Despite this wealth of easily available data, it is still difficult to reproduce the results of many research papers without significant effort. Though there is a generally increasing trend of releasing data in code, not all works provide theirs. Many evaluations boil down to validating the reconstructed appearance for a few unseen camera or light settings. What is missing are extensive comparisons to other methods. This is because the high re-implementation effort of existing methods without code release is usually not justified for comparison purposes only. So comparisons are often selective to those methods that have data or code available. This, on the other hand, prevents conclusive assessments of the reconstruction quality, which is in contrast to many other fields of graphics and vision. So far, the wealth of new material sources has come without significant developments regarding standardized benchmarking. The motivation for our work is this lack of benchmarks for appearance modeling. Benchmarks help maintain good scientific practice through standardized testing. Let us first define what we want our benchmark to be like. It should contain measurements of real-world reflectance. Though synthesized materials reach a high level of realism, they are often still missing the final grain of variations and imperfections to make them indistinguishable from real physical samples. Most real surfaces show spatial variations, so the samples in the dataset shouldn't be spatially homogeneous. And last, the material samples should cover a wide range of appearance variations. For this reason, we select fabrics as type of materials. Furthermore, we would like to pose the benchmark as a competition. Such competitions have grown popular during the last years. See, for example, the entire super resolution and spectral reconstruction challenges at CVPR. Here our motivation is to attract further attention, potentially even from other fields. To create a fair competition setting, we need to ensure to build it on previously unpublished data. Now a brief overview of existing datasets. In 2013, Bell et al. Published the Open Surfaces dataset consisting of real-world photographs annotated with BRDF parameters per object. In 2017, these spatially homogeneous BRDFs were used by Kim et al. In their SynBRDF benchmark, consisting of renderings of complex geometries under varying natural illumination. The dataset is more interesting for in the wild settings, where reflectance, illumination, and camera pose are unknown. We want to put the focus on appearance modeling only by using geometrically and radiometrically calibrated images of reflectance. Over the years, several other datasets of homogeneous BRDFs were measured. However, we consider heterogeneous surfaces the more realistic and challenging setting. Such datasets exist. Deschantre et al. Generated a large-scale dataset based on 155 procedural SVBRDFs from Substance Share, which they randomly perturbed and combined via blending to obtain 20,000 material samples. Lee et al. Rendered a select under environment illumination. Such datasets have in common that their renderings are obtained by evaluating BRDF models, which can cause a lack of realism. More desirable are image-based measurements of reflectance. Such measurements can be found in BTF datasets. However, BTFs are not suitable to represent arbitrarily glossy materials because of resampling artifacts or the need for an infeasibly high angular sampling. More suitable are direct, non-resampled images of reflectance, as published in our previous UBOFAB 19 dataset. However, all of these datasets have in common that they are fully released, which rules out using them in a competition. We extend the UBOFAB19 SVBRDF dataset by 56 new materials acquired by X-Rights Tech 7. Each material consists of 768 radiometrically calibrated HDR images. We try to cover a wide range of appearances by picking materials of several different colors, gloss levels, pattern complexities, or fabric types, such as brocades, embroideries, satin, and so on. We publish the measured images and all relevant calibration data as our new AppBench dataset, which is already available for download. We hold back around 10% of the point-lit images for evaluation purposes in the benchmark. These images are selected to cover a representative set of light and camera directions. For this holdout set, we only provide the directional sampling per pixel. Competition participants have access to the public part of the AppBench dataset, which they can use together with, for example, UBOFAB19 to develop their models. They then have to evaluate these models for each AppBench material on the directional sampling of the holdout set. After uploading their reconstructed images to the competition server, an automatic metric evaluation and ranking is performed. We use a set of standard image metrics for assessing the quality and rank according to the mean absolute deviation. As the measured fabric samples are not perfectly planar due to mesostructure, the observed reflectance contains non-local effects like interreflections and shadows. In a second branch of the competition, we intend to reduce the contribution of these effects by applying pixel-wise weights. For this, we apply confidence weight maps before applying the metrics, followed by a normalization. The weights are calculated as the product of the cosines of the angle between the light direction and normal and the angle between view and normal. This scheme, which is also known from perceptual BRDF similarity metrics, assigns lower weights to grazing angle configurations, thus modeling their increased uncertainties. Additionally, we compute a visibility term via ray tracing that masks shadowed or occluded pixels. As a first baseline submission, we use WARD SVBRDF fits produced by X-Rights Pantora software. In the future, we plan to submit additional baselines, for example Pantora's energy-preserving GGX model. We host the competition on the CodaLab platform, which provides user management, automatic evaluation, and ranking, code samples for reading the database images and calibration data, as well as an example evaluation script are provided as a starting kit to ease participation. The competition is ready for participation. We are open for suggestions about relevant metrics and baselines. In the future, we intend to extend the dataset by new material categories.
Okay. So thank you for that presentation. And I think this is quite an exciting development. I'm waiting to, yeah, there's a bunch of people typing in here. So I think we'll get a question here soon. Is the competition on entirely new materials or on unseen directions for the same material?
The latter is the case, yeah. So the set of materials is both published on our website, but we also hold back a bunch of the images. And for those same materials, the competition participants have to recreate these images.
And yeah, once again, there's like a furious amount of multiple people typing, so I don't want to miss the questions. Roughly, what is the resolution pixel pitch spatially and angularly?
So spatially, we have cropped the materials for practical reasons during the evaluation, so it doesn't exceed time limits to 256 squared pixels. Given the Tech 7 spatial resolution of, I think, 15 pixels per millimeter, you can do the math. And angularly, in my slides, I showed that this one material set is captured with around 768 images using the preset we used for fabrics. which is composed of these different types of modalities. So it's quite difficult to answer this. But for the point lit images, we have around 288 individual combinations of light and view directions, where we have four dedicated cameras, and then accordingly these roughly 30 LED lights, which are turned on under different rotation stages.
Okay, there's for people who missed the link that you can look in the Rocket chat there. And an important point is this includes spectral data or only RGB?
No, the images we publish are RGB only. The TAC7 measures spectrally with 10 bands, which are used to reconstruct around 31 channels in the visible spectrum. But again, for practical reasons, we limited this to RGB only, especially because the post-processing pipeline by default works in RGB, and it takes a bit of fiddling to interfere there and get spectral data out of it.
Okay, I'm not seeing, oh, I do see typing, so I'll wait a sec here. So for another question.
Maybe to connect to Christoph's question, so
yeah.
Using spectral data is certainly something we can think of for the future for extending this benchmark to make it more interesting.
Yeah, so I think, well, I do think in the last general session, we want to talk a lot more about benchmarks, this benchmark in particular, and needs for benchmarks. But to keep semi on schedule, I think we'll go to the last presentation, which will be from Morgan McGuire. And so we'll go to that presentation, and then we'll be back for Q&A.
Hello, I'm Morgan McGuire, and I'm presenting a collaboration with Julie Dorsey, Eric Haines, John Hughes, Steve Marschner, Matt Pharr, and Peter Shirley on a taxonomy of bidirectional scattering distribution function lobes for rendering engineers. With the word engineer, we intend to include researchers, faculty, and students, the people who design rendering systems and build them. But that's different from the scientists and engineers in adjacent fields, people in manufacturing, and content creators who have different needs and are going to have their own taxonomies for which ours might not be appropriate. Several months ago, Pete gathered us all online. He noted that there's a lack of consistency in the terminology that we use to describe materials in computer graphics rendering. He proposed that we standardize for our own future textbook editions for our courses and papers in order to reduce that confusion. So we surveyed the major work across several fields in 5 decades, and we sought to find a reasonable set of terms and concepts for materials. The first challenge we noted is that material has many different meanings in the field of computer graphics and interactive techniques when it's taken as a whole. A material could describe the properties of physical simulation, including density and chemical properties, friction coefficients, and rigidity. It could be an audio material, which includes the sounds that an object makes when it's struck with different materials. A material could be a modeling material, which includes shape and detail features like fur and tiles and bumps. For many of us, surface rendering for the outermost surface is what we care about. Or maybe we mean multiple thin layers of the surface as the material, but that can include emission as well as light reflection. There's also the process of volumetric rendering for things like fog, and that includes phase functions in the material. And then if you went to a gameplay designer, they would say that in the game logic, the material includes properties like, can this object be picked up by the player? Is it breakable? Can it be traversed by a non-player character? So there are many, many definitions of material. They all include an overlapping set of properties, and they get tagged on objects, but it wasn't something we could usefully build a taxonomy for our purposes. So this is a problem. And to illustrate it, let me show you, if you have a sphere with a particular material on it, I personally picture something like this, where the color and the size of the highlight are sort of the space of variation in material. But that's what a sphere looks like with a red rubber material maybe. But to an artist who's using a tool like Substance Designer, that artist might say these are all the same geometry, the same object. It's a sphere, but they have different materials. And coming at this first from a rendering perspective, I hadn't thought about, for example, in that second example, the coverage mask in the wicker example being part of the material. But that sort of makes sense, although I like to think of it as that's the absence of any material. But that the material might include the displacement map, or if we look at that final sphere, it looks a little bit like a globe. That actually has individual procedurally generated sailboats and houses inside of what it's considering the material on a sphere. And to me, that's clearly into the realm of geometry. And so obviously, throughout our field, people really disagree on what exactly is material. So we decided to address this by narrowing our goal from describing materials to describing appearance under thin surface rendering at the level of uniform small patches within a pixel or texel. And yet, we still found the terminology for appearance to be inconsistent. I think probably the most common definition problem in all of rendering is, what does specular mean? And to some people, that's a surface that creates a perfectly sharp mirror reflection. And to others, it's a surface with mirror reflection or refracted transmission. And then to many others, it's any blurred reflection that's going to be sort of near or driven by the mirror reflection direction. So those are very different definitions. And of course, if you then went to, say, vendors of paint and metal and cloth, or to optical physicists, to natural media artists, to CGI artists, to game programmers, to VFX engineers, academic researchers, all of these groups have different words for describing the appearance of something like this shiny statue, even when they're just talking about appearance. We're not even trying to categorize material anymore. And furthermore, we recognize that we really can't discuss appearance as a property of an object anyway. And that's because the passive appearance of an object results from many factors. There's the combination of the two media, one on either side of the surface where light is scattering. So this includes air in this cartoon. The incident illumination conditions, the imaging system has different sensitivities, such as a camera sensor or a human retina will affect appearance. And then the context within the image, so things like light adaptation, bloom, and local contrast, both in space and time, all those happen in the human visual system, and they happen in modern cameras and computer graphics cameras as well. And when I say passive appearance, I just mean the object isn't emitting light itself. That's a whole other issue. So our conclusion from that thought process was to actually abandon trying to define materials and appearance at all, and focus on something else. So appearance is the result of shading. We're better served in rendering by describing the key actor in shading, which is the bidirectional scattering distribution function, which is abbreviated BSDF. And that's not a property of an object, actually. It's an emergent property of an interface between two optically homogeneous media. In practice, it is common, though, to assume that the surfaces will be in air and to attach a BSDF to specific geometry or to an object. But we want to recognize that that's not true in the general case. The BSDF will change with the surrounding medium. So here's what the BSDF is. It's going to be a function of the incoming and outgoing direction vectors at a surface. It's the ratio of change in outgoing radiance to the change in incident radiance over small solid angles. It has units of per steradian, and this means that the BSDF is a distribution of light scattering in every possible direction. So numerator radiance, denominator irradiance. And if I choose some incoming direction of light, then I could visualize a cross-section of the BSDF in 2D with a cartoon like this. The gray box is going to be a medium, such as glass, and the top of the box will be the interface between air and that glass. And let's, to make this interesting, say the glass is rough. It's going to be ground glass, sandblasted. The blue arrow is the incoming direction of propagation of the light that I've chosen. And this normally would vary over a theta and a phi, or over x, y, z. So it's 2 degrees of freedom. I'm fixing it for the picture. And then here's the distribution of scattered outgoing light. And for the ground glass, there's probably a lot of reflection around the mirror direction, but a fair bit that scatters in every direction. And then there'll be some that propagates forward into the glass by transmission, but it'll be diffused by that rough surface, which is why if you have rough sandblasted glass, it provides some privacy on like a shower door by blurring what's seen through it. So in order to draw this, again, I had to fix both degrees of freedom for the incoming vector, and then 1 degree of freedom for the outgoing vector, and that left only the outgoing angle on the plane of the screen that I had to graph relative to. If I chose the incoming direction differently, or a different orientation for the diagram, then we'll see a different distribution. So if I maybe look at that direction, I get a different distribution, different distribution. Now, in practice, a rendering system mainly uses a BSDF in 2 ways, and I'll illustrate those with sort of toy renderer pseudocode. On the left here, you can see code that evaluates the BSDF function for direct illumination. This is what happens in a rasterization pixel shader or an array hit shader. This is what everyone spent a lot of time on in the early 80s. Systems using rasterization continue to spend most of their computation time on that until recently. But what's more important today and going forward is on the right, this is the code for a mock path tracer. That's a Monte Carlo renderer. And it's going to sample directions, sample the outgoing light directions with a probability distribution that's proportional to the BSDF. And in practice, if you're doing a good job, it should be proportional to some other things too, like maybe the cosine of the angle of incidence and the incoming light distribution. But at the very least, you're going to care about this BSDF as a distribution. And sampling is where the computational research emphasis today is for offline rendering, and increasingly that's also the case for game rendering with real-time ray tracing and stochastic methods. And the sampling use case is also the primary motivation for today's talk, as we'll see in a moment. Unfortunately, the BSDF terminology in the literature isn't much better than the appearance terminology. In fact, it's mostly the same terminology. So it seems like we haven't made much progress, but now we're actually at the point where now we can make a contribution. Now we can introduce a taxonomy. And in order to come up with the taxonomy, it's important to first step back and ask, why do you want to name things? Why do we want to distinguish cases? Because it's an interesting theoretical and intellectual exercise, but it's hard to get an objective place to distinguish between cases if we can't first articulate why we're trying to do that. And this is, I think, one of the key insights in our work as a process, and this is why I think we're going to have some success with our taxonomy. We notice that when we are creating code or algorithms, we have procedures, methods, functions, we need to name them when we use and implement BSDFs in different ways. And we notice that we sort of factor the code itself into different helper functions. And so let's look at why we make those separate functions and the separate classifications, and that will justify branches of the taxonomy. When a renderer is sampling a BSDF, it has to handle light scattering differently, depending on whether it's described by a discrete or a continuous probability distribution function. On the right, we're showing a schematic of a PDF probability distribution function for a surface that always produces a discrete set of light rays from one incident light ray. So for example, a perfect mirror. And then there's some photographs shown of interfaces between glass, very shiny metal, or water and air that could be approximated by such a BSDF. Now, the BSDF for a mirror reflector isn't a function in the mathematical sense that we're used to. For every input, it evaluates to either 0 or infinity. Consider that in the context of our two main use cases for BSDF, evaluation for direct illumination or sampling for Monte Carlo ray tracing methods. It is not useful to evaluate the mirror reflector BSDF for direct illumination. The result will either be infinity, which we can't use for shading, and that's only going to occur for a single direction, and thus with zero probability anyway, or the value is 0 because we're not at the impulse direction, and so there was nothing to compute if the answer is 0. And so in either case, it's not of any use. So we'd like to classify such BSDFs so that we can branch in the code and exclude them from direct illumination shading. Now for the sampling use case, when we have this kind of distribution, we need to employ discrete, which is probability mass sampling algorithms, instead of continuous probability density sampling algorithms. And so we, once again, require a code branch. This is the implication of Monte Carlo for the taxonomy that I promised you 2 slides ago. So this branch point in the code where between continuous and discrete, we implement the actual method in our code differently, that creates a branch point in the taxonomy. We need to have names for those branches to refer to that part of the algorithm. For the case where the single incident light ray produces a continuous distribution on the left, we can further subdivide the scenarios, and that's again going to be driven by the Monte Carlo considerations. Outgoing rays that are sampled proportional to a continuous distribution can either be clustered together and probably highly influenced by a particular outgoing direction, or they could be spread out widely over many directions. When the rays are clustered together, that creates a very coherent raycast, and that encourages certain kinds of data structures and scheduling operations for parallel processing that computes the ray intersections. Monte Carlo's renderers use stochastic samples, and that produces noise in the final image because of the randomness of the low discrepancy sequence. And so a common step in rendering is denoising by blurring together the contributions of nearby samples in an image or samples from previous frames that we expect should have had similar values and because the Monte Carlo process diverged. When denoising animation, knowing that the outgoing rays are clustered together tells us that we should not blur too far in screen space. Knowing whether retroreflection, transmission, or the mirror vector most strongly influences the BSDF shape also tells us how to blur contributions from the previous frame into the current one. For the case of rays that are spread widely, we need a very large denoising kernel, since there'll be a lot of noise, But it also tells us that we can reproject samples directly onto the surface as they're less dependent on the view direction. And finally, we can further divide the spread out case. When the relevant distribution is uniform over the hemisphere, that's a special case that allows pre-integration, as the incoming direction is irrelevant. We can also perfectly reproject during denoising. The remainder of the spread out case is everything else. It has no special properties to exploit. It also avoids the singularity of the mirror case, so it must be handled in a fully generic way. Now, most of the time we can't describe a BSDF using just one of these categories. Instead, the shape of the BSDF is expressible as a sum of these. So measured or simulated BSDFs can be projected onto these terms as a kind of basis space. Because one category is everything else, there's not going to be any error in approximation by doing so. And so we decompose into a sum of lobes. If you have an artistic or a fitted analytic BSDF that's already been separated into weighted terms by construction. And so all that's left is just to name the different shapes that appear in our functional decomposition diagram. So the space of all composable BSDF lobes, when we have to branch on the sampling implementation, we name the perfect mirror in related cases impulse or perfectly specular, and we name everything else finite valued. When we have to branch on lobe orientation for clustered together distribution, we say it's retroreflective if it's strongly influenced by the incident direction, glossy if it's strongly influenced by the mirror direction or the refraction direction, and we call everything else diffuse. And finally, when we have to have different pre-integration strategies, we call Lambertian or perfectly diffuse the view-independent constant BSDF case, and then everything else is just general diffuse, which is subsumed by the diffuse category. Here's a list of all the terms that we specifically define in the paper. You can refer to the paper for those. The paper also contains sort of Rosetta Stone relating our terms to previous terminology that's popular across adjacent fields. So in summary, we hope everyone will adopt and extend our taxonomy, but at least for ourselves, now we can have consistent terms in our libraries, our textbooks, publications, and courses. The methodology that we arrived at is one that I'll now use for creating terminologies and taxonomies in general, which is define the input, not the output, distinguish where there's an implementation difference, and that's where we put the branches, reuse terminology that's already in use, but retroactively define it so that it's now clear and unambiguous. We really encourage further work on standardization to make interdisciplinary communication more effective and to make graphics more accessible to newcomers. Thank you very much.
Okay, thank you for the presentation and the great stick figures. I think there's some questions, well, there are comments showing up, and actually I didn't recognize everyone in the diagram, but one question was about, in general, whether the MAM papers are posted in the EG library yet. They will be after the event, because our normal procedure in MAM is to have some discussion after the presentations, and then the authors can update their papers according to that discussion. And on the other hand, if you need this one right away, we can, there is, a full paper was submitted. So I'm sure Morgan would be happy to send you a copy if you need one earlier. So, but it'll be probably about a month before everybody gets their updated version, and then it will be in the digital library. Other people are typing, so. I guess while I wait for the questions to come up, are there other areas of terminology that need to be straightened out, or does this do it for us for materials?
Well, this is a great question, Holly. One of the things that we mentioned sort of in an aside in the paper, that layered means different things. Layered BSDF to game developers and to the VFX and academic side. So for game developers, it means something like rusted metal, where you would have two separate BSDFs and you would mask them together with like an alpha channel. And to the academic and VFX community, a layered material is something where there's sort of translucent layers, so such as varnished wood, where the different physical layers are interacting with each other. And I think that causes a lot of confusion because we're reading the same literature now, and we mean different things by it. And there's also just all the mathematical notation is different across materials, as well as BSDF, submission functions, phase functions. I think that's challenging. And then, throughout graphics in general, there's obviously a lot more opportunities. But for materials, we found so many places where there was inconsistency that this was the piece we could tackle was the BSDF for rendering engineers. But we would love to see sort of more common terminology, for example, on the expressive side for artists, so that we could have parameters labeled the same things in every tool.
Although as for artists, it's not clear that we want the same parameters, and what the right parameters are is still like the mathematical formulation of them isn't even known, I would say, but we can argue about that. Okay. A comment is the taxonomy seems pretty consistent with existing ones. A new term to me was impulse, whereas previously people have used delta or singular. It's a matter of just like, we got to choose one.
So we definitely, we didn't want to invent words if we could avoid it. So all of the words we're using should be very familiar. And I think what's unique is that we're tying those to physical phenomena, so that there's an understanding between the physics and optics literature and what we're doing in graphics. But then also that we've sort of retroactively assigned definitions to these that are objective, clear mathematical definitions. So for the impulse case, that was one of the ones we said impulse or perfectly specular. We're going to treat those as synonyms, but that we wanted to really define that and make it different than specular is this really ambiguous term that a lot of folks use. And so perfectly specular means something now under our taxonomy. The word specular alone is simply not used without a modifier.
Okay, I wanted to note that I guess it's a link that was posted to your slides are already online. Is that correct?
Yeah, so we went ahead and put the slides, and we put a preprint of the paper. We're going to edit based on community feedback for the final version of the paper, but we wanted to get everything out there so folks could discuss it.
Okay, great. Yeah, so everybody do take note of that so that you can look at it and send in comments, because I mean, that is the rationale for posting the papers afterwards. More of a comment than a question from Wenzel. One frequent source of terminological confusion occurs in the world of participating media regarding the quantifier anisotropic. For instance, Heine-Grenstein phase function is considered anisotropic, but microflakes and other models developed in computer graphics are even more anisotropic. Yeah, I think, that is, the whole subsurface scattering participating media is a whole nother region that needs some precision, as like you say, the media versus the phase function and differentiating.
And I hope that
being clear about that.
So Holly actually contributed behind the scenes to a lot of this discussion. She didn't co-author the paper because she was chairing the conference, I think, so she didn't want the conflict of interest. But I'm hoping that Wenzel and Wojtek and Holly could write the phase function equivalent of this to extend this work. Would be great next year.
Well, I mean, thinking about this does tie back to David's presentation about, we don't even know, like, and trying to describe the physical stuff that we're tying the perceptual stuff to is still, and even in radiative transfer, I mean, you can say, extinction and the albedo, and you can, different ways, or you can just have scattering and absorption. It needs to, we need a good playbook. I mean, and this is also all this stuff is really important also when you have a new colleague from optics and you spend, the morning like, well, I call this, what do you call it? And, so every time you meet somebody from another discipline, you can at least hand them this, and then they'll have a little code book for understanding what you're saying.
Absolutely. My current team, a lot of our research is based on psychophysics, and I think there might be only one or two computer science PhDs. It's physicists, neuroscientists, psychologists, EEs, mechanical engineers. And we spend half of every meeting just saying, well, when you said coherent, what did you mean? When you say color, what does that mean? And so I think that's the future of computer graphics, though, is really starting to bring together the manufacturing, the physics, the perception, the art, as well as the simulation side that was sort of
but I think putting them, they're not all in one basket. So having, saying what does this vocabulary apply to is important. There are more comments coming in that some extensions to describe properties of phase functions, since a phase function is conceptually very loosely like a BSDF to a full sphere, seems like a good step. A material can be isotropic in the 2D tangent plane, but the resulting BRDF is always anisotropic in 3D. Noting that a few years ago, I tried from Stephen Hill, I tried in Vine to convince a DCC material tool company not to use the word layering to mean parameter blending. Now games real-time is increasingly using layered material models. And that use of, Natty points out, that use of layers is not unique to games. Yeah, I guess you all can read the comments. I'm in there looking for a question so that I can organize the discussion with Morgan. But the fact that there is all this back and forth tells me that it's time for us to move into the big Zoom room where everybody gets a chance to speak, not just the speakers. And so what's going to happen is we don't want to, of course, broadcast the Zoom room to the whole world. Tobias, you're going to post in the Rocket announcements, or no, general, hashtag general.
I'll post it wherever I can, Ollie. Yeah, and nobody can miss it except the YouTube chat. There I won't post, but for everything internal, people can get the information.
Okay, because right now I don't see it anywhere.
Well, I didn't do it yet. I have to do it after we complete.
Okay. So look in the general and the announcements for EGSR, and very shortly there will be a Zoom link, and let's all go there and we'll have a group discussion on this and all the other various things that have come up. So I'll see you over there in a couple of minutes, I guess. Okay, thank you.
Thank you, Ellie.